Hello students, in the previous video we discussed the Lewis concept. We discussed how to make ionic compounds and covalent compounds on the basis of Lewis theory. Lewis theory is also known as octet rule. So according to that concept, every element tries to complete its octet. That it can do either by transfer of electron or by sharing of electron. Now today in this video we'll discuss the next theory, which is also related to bonding, and the theory is valence shell electron pair repulsion theory. In short, it is known as VSEPR. Now this theory mainly deals with the shapes of molecules. This theory will not explain that how a bond is formed, but this theory will explain that after the formation of bond, what shape or what geometry the molecule will acquire. So according to this theory, we can know the shapes of different molecules. So today we'll discuss this VSEPR in detail. Now, what are the main important points of this theory? The first point says that the shape of a molecule depends upon the number of electron pairs around the central atom. Now, these electron pairs can be bond pairs as well as lone pair. So the shape or the geometry of molecule depends upon the number of electron pairs, or we can say the number of valence electron pairs surrounding the central atom. Now these electron pairs can be bond pairs as well as lone pairs. We have seen while we made the Lewis symbols, the central atom in the molecule is surrounded by bond pairs and lone pairs. So those electron pairs will decide the shape of molecule. Now how it is done, let's see. Now the second point says that the electron pairs which are surrounding the central atom, whether they are bond pairs or they are lone pairs, they try to repel each other. Now why they will repel each other? Because the electrons are negatively charged. So these electron pairs will repel each other. Now since the electrons are negatively charged, the electrons will repel each other, and these electron pairs will try to move apart and will tend to occupy those positions in space where the repulsion is minimum, or we can say the stability is maximum. Also, the magnitude of repulsion is different for different type of pairs. For example, lone pair repulsion is highest, then lone pair bond pair repulsion, and lastly bond pair repulsion. And when the electron pairs move apart, they occupy such positions, they are fixed in the space, and that fixed positions give the geometry of molecule. So the electron pairs get fixed at a particular space, which gives a geometry to the molecule. And what is that particular space? The particular space is that where the repulsion is minimum. Okay, and this is all about your valence shell electron pair repulsion theory. This theory does not distinguish between s electrons or p electrons. This theory counts only the total number of valence electrons surrounding the central atom. So now we'll discuss the examples, that how different types of molecules have different shapes, what are the shapes of molecules. So let's begin with the theory. Now let's begin with the theory. Suppose now this is a table. The first column is number of electron pairs surrounding the central atom. The second column is how many bond pairs are there. The third column is how many lone pairs are there. And the fourth column is the geometry or the shape and the examples. The first we'll discuss, suppose the total number of electron pairs around the central atom is 2. Okay, the central atom is surrounded by 2 electron pairs. Both of them are bond pairs lone pair is not there. Okay, so the central atom is there, which is surrounded by two bond pairs. Now in such cases, what is the geometry or shape of the molecule? Suppose A is my central atom. Now A is surrounded by two bond pairs. Now the two bond pairs will occupy such positions where the repulsion is minimum, and such positions are at an angle of 180 degree. Okay, this is the first bond pair, this is the second bond pair. So the two bond pairs will occupy such positions where the repulsion is minimum, and this angle is your 180 degree. So it is found that when the two bonded atoms, this is the first bonded atom, this is the second bonded atom, when the two bonded atoms are at an angle of 180 degree, the repulsion is minimum. Now what is the geometry in this case? You can see the geometry or the shape is linear or straight. Now what is the example in this case? So the examples are, first example is BeCl2, the second example is BeF2, the third example is carbon dioxide. All these molecules have this type of shape, that is linear. So I can make, now this is my central beryllium. I can explain one example. Now this is first bond pair to fluorine, we can say. This is second bond pair to the fluorine. Okay, now beryllium has only 2 electrons in the valence shell, so it has given 2 electrons. Now fluorine has 7, so 1 it has given, so remaining will be 7 now. Sorry, 6. Okay, fluorine has 7 electrons in the valence shell, 1 electron it has given here. So how many electrons will remain? That is 6. So you can see that there are no lone pairs on the central atom. The surrounding atoms have lone pairs. But this theory does not take into account about surrounding atom. This theory takes only central atom as the main. So this is the first case, that the total number of electron pairs are 2 and 2 are bond pairs. Now the second example that we'll take is the total number of electron pairs are 3 now. Means 3 electron pairs are surrounding the central atom and 3 are bond pairs. No lone pair is there. Still we have not taken lone pair into account. Okay, still we are discussing the cases with bond pairs only. So 3 electron pairs are there, 3 are bond pairs. So let's see, suppose A is my central atom. Now which geometry or which shape will give them minimum repulsion? So it is found that when they are at an angle of 120 degree. Okay, now this angle is 120 degree. So when the 3 bond pairs, now these are 3 bond pairs, when the 3 bond pairs are at an angle of 120 degree, the repulsion is minimum. Now what is the geometry or the shape of these molecules? Now I can do like this. Okay, the dotted line gives us the picture of shape. Now it appears in the form of triangle. Okay, this is not bond. I have joined them to give an idea about the shape. So it is in the form of triangle. So the geometry is trigonal planar. What is the geometry or the shape? Trigonal planar. So when total number of electron pairs are 3, 3 are bond pairs, the geometry or the shape of molecule is trigonal planar. Now we can discuss examples here only. Now what are the examples in this category? Now in this category the examples are belonging to group 13, that is BF3. Okay, boron has only 3 electrons in the valence shell, BCl3, like this. So these examples or these molecules have trigonal planar geometry and the bond angle is 120 degree. Now let's move on to the next, that is the total number of electron pairs are 4 now. The 4 are bond pairs, 0 lone pair is there. Now in this case, what should be the geometry or the shape of molecule? Now we have to assume that shape where the repulsion is minimum. And this type of shape is found to be like this. Suppose this is your central atom. 1, 2, 3, 4. These are my bonded atoms. 4 bond pairs are there. Now I will join them so as to give the shape or the geometry to the molecule. Now this shape is or geometry is tetrahedral. Okay, and the bond angle here is 109 degree 28 minutes. Now what is the meaning of bond angle? Bond angle means angle between the bonded pairs. Okay, because again and again I am telling that this bond angle, this bond angle. So what is the meaning of bond angle? Angle between the bonded pair of atoms. So this will be 109 degree 28 minutes. This will be 109 degree 28 minutes, like this and like this. All the bond angles are equal. So when the two atoms are this much apart, then only the repulsion is minimum. Now this tetrahedral geometry is three-dimensional geometry. Okay. Now this tetrahedral geometry is like this. Now these two bonds are in the plane of paper, like this. Okay. The blue and the green pen is in the plane of paper. The pink pen is back side, means back of the paper, away from the observer, and this pen, okay, white pen is towards the observer. So this tetrahedral geometry is three-dimensional. These two bonds are in the plane of paper. Angle is 109 degree. This bond is towards you, that is towards observer, and this bond is away from the observer. Now what examples are there in this tetrahedral geometry? Let's discuss. The best example is your methane, CH4. All the elements belonging to group 14, they have 4 electrons in the valence shell, so they will make 4 bonds. CH4 is there, CCl4 is there, SiCl4 is there. So these are the examples which are included in this category. One important example is NH4 plus also. Ammonium ion. Okay, ammonium ion means nitrogen has 5 electrons in the valence shell. Now one positive charge is there, so it has now only 4 electrons, so it also has tetrahedral geometry. Now in tetrahedral geometry we'll start with the lone pair. Till now we have not taken lone pair into account, but now with this geometry we'll start with the lone pair. So total number of electron pairs are 4. 3 are bond pairs and 1 lone pair is there. Now let's see what is the geometry and the shape. Now remember one thing, since the total number of electron pairs are 4, the geometry will be tetrahedral only. So geometry is tetrahedral. Okay, now tetrahedral geometry means all the 4 positions will be like that only. So this is my central atom. Now what are the 4 positions? 1, 2, 3 and 4. These are the 4 positions. Now in the 4 positions, 3 are bond pairs and 1 is lone pair. So any 3 positions can be occupied by bond pairs and any 1 position can be occupied by lone pair. I can make this as lone pair, this as lone pair, this as lone pair, or this as lone pair. Suppose I am making this as lone pair. Lone pair is shown like this. Okay, now this is the shape of an orbital, you know, and 2 dots are there. Okay, so this is the symbol for lone pair. So I have made here lone pair. So now this is the molecule having 3 bond pairs and 1 lone pair. Geometry is still tetrahedral. Okay, now listen one thing carefully. When the molecule has only bond pairs, the shape of the molecule or the molecule is said to be symmetrical. Symmetrical means the repulsions are less, because we know that the bond pair repulsions are very less. So such molecules are said to be symmetrical. They have symmetrical shapes, they are symmetrical in nature, or they have regular geometry. No lone pairs are there. But as soon as the lone pair comes, repulsions increase, because we know that the magnitude of repulsion between lone pair and bond pair is more. So now repulsions will increase, and the geometry of the molecule is said to be irregular, or we can say it is now distorted. Not symmetrical, irregular. Okay, and in this case we write the shape. Now what is the shape of molecule? Geometry is still tetrahedral because geometry is decided by total electron pairs. Now what is the shape of molecule? The shape is decided by only bond pairs. Okay, now in order to find the shape of this molecule, hide this lone pair. So if we hide this lone pair, it is looking in the form of a prism. Okay, so what is the shape of molecule? It is pyramidal. In the form of pyramidal, it is looking like. So when the molecule has only bond pairs, the geometry is symmetrical, regular, less repulsions are there. But when the lone pairs are also there, then geometry and shape, two different things are there. Geometry is decided by total electron pairs, okay, and shape is decided only by bond pairs. Now what will happen as a result of this lone pair? The repulsions are increasing. And when the repulsions are increasing, what will happen? Now this repulsion will increase. This repulsion will also increase because lone pair is repelling now bond pairs. As a result of this, this bond angle will also change. Okay, earlier the bond angle in tetrahedral geometry is 109 degree and now the bond angle will be reduced to 107 degree. So this is 107 and this is 107. We don't calculate the bond angle between lone pair and bond pair. Okay, bond angle is always calculated between bond pairs. So why the bond angle is reduced? Because of the repulsion. Okay, because of the presence of one lone pair, now repulsions are increasing, so bond angle will be reduced because now these bond pairs will come closer because of these two repulsions. Now what is the best example in this case? The best example is your ammonia. Okay, this is nitrogen. It is having one lone pair and three bond pairs are there like this. The best example is your NH3. Okay, total 5 valence electrons are there, so 3 are bond pairs and 2 are lone pairs. Other examples can be NF3, PCl3, like this. So now we have seen that as lone pair is there in the molecule, the repulsions increase. Okay, the position of the bonded atoms change, the shape of the molecule changes. Here the geometry is also tetrahedral, shape is also tetrahedral. Here the shape of the molecule is now changed to pyramidal. So pyramidal is the shape of the molecule. Now the total number of electron pairs are 4. 2 are bond pairs and 2 are lone pairs. Now I am increasing the lone pairs and decreasing the bond pairs. So if A is my central atom, now there are 4 positions. The positions will be in tetrahedral form only. So these are the 4 positions in tetrahedral. Now at 2 positions I have to write lone pair. So this is first lone pair. You can choose any position. It's up to you. I am choosing these 2 positions. Now this is first bonded atom. This is second bonded atom. So when 2 bond pairs are there and 2 lone pairs are there, they will occupy positions like this. Now still the geometry is tetrahedral only. But now the shape is different. And how to find out the shape? Just hide the lone pairs. So if we hide the lone pairs, it is looking in the form of V shape. Or we can write angular also, bent also. So this is the shape of molecule. And what is the consequence on bond angle? Now repulsions are further increasing. There will be repulsion between lone pair and lone pair. So these 2 will move apart. Now this repulsion is there and this repulsion is there. The magnitude of repulsion has increased 3 times. So what will happen? These 2 will move close. As a result, the bond angle is further reduced to 104 degree. And what is the example in this case? The example here is water. H2O, H2S. Okay, water has this type of shape. Oxygen atom, the oxygen is the central atom, 2 bond pairs and 2 lone pairs. The bond angle is 104 degree. So we have seen that in total electron pairs 4 or tetrahedral geometry, the bond angle is 109 degree if it is regular. The bond angle reduces to 107 with 1 lone pair, and if 2 lone pairs are there, it is further reduced to 104 degree. Okay, now we'll discuss only up to 2 lone pairs, because if 3 lone pairs are there, then the repulsions will increase so much that the molecule becomes unstable. So here we'll discuss only up to 2 lone pairs only. Now the next is total number of electron pairs are 5. The 5 are bond pair, 0 lone pair is there. Now when the total number of electron pairs are 5 surrounding the central atom, so A is my central atom. Now 5 electron pairs are there. So what are the 5 positions? First, second, third, in the form of triangle. I will join them. So this is 2D on paper. One bond is like this and another bond is like this. Means one above the plane of paper and the second below the plane of paper. So this geometry is like this. This triangle is in the plane of paper. One bond is towards you and one bond is away from you. These 3 bonds which are lying in the plane, they are known as equatorial bond. Angle is clear, it is 120 degree. And these 2 bonds which are above and below the plane, they are axial bonds. And angle is clear, it is 90 degree. Now what is the name of this geometry? This geometry is known as trigonal bipyramidal. Okay, trigonal bipyramidal. This is triangle. One bipyramidal means one pyramid is up and one pyramid is down. So this is your trigonal bipyramidal geometry. Now total electron pairs surrounding the central atom are 5. 5 are bond pairs. 3 are equatorial bonds and 2 are axial bonds. 3 bond angles are 120 degree and 2 bond angles are 90 degree. Now this is against your octet rule because the central atom is now surrounding by 10 electrons. So this is an exception to octet rule. Now what examples we'll discuss here? The best example is PCl5, phosphorus pentachloride. It is like this. 3 chlorine atoms are here, equatorial, 1 chlorine atom up and 1 chlorine atom down. 3 angles are 120 degree and 2 angles are 90 degree. And the geometry is trigonal bipyramidal, or you can say the shape is also trigonal bipyramidal. Now we'll discuss lone pairs here. Okay. Now the total electron pairs are 5. Now 4 are bond pairs and 1 is lone pair. Now the geometry is not regular. It is not symmetrical. It is distorted now. Now geometry will remain trigonal bipyramidal only. But the shape will change. So this is central atom. 1, 2, 3, 4, 5. Okay, these are the 5 positions. Let's join them. Now where to put the lone pair? Lone pair is generally kept at that place where the repulsion is less, because lone pair causes more repulsion. Now these 3 are equatorial positions. These 2 are axial positions. Lone pair is always kept at that position where it repels less. And it is found that when the lone pair is at equatorial position, less repulsion is there. So we'll keep the lone pair at the equatorial position. You can keep lone pair here also and here also. I am keeping the lone pair here. Okay, now the remaining are bonded atoms. The geometry is still trigonal bipyramidal, but the shape is different. Now hide the lone pair. It looks like in the form of K. So we can write K shape. We can write pi shape also. Okay, it is in the form of pi, or seesaw shape. So this is the shape of molecule. Now what are the example here? Now the example is SF4. It is like this. The sulfur is the central atom. One lone pair is here. You can keep lone pair at any place. It's up to you. I am placing it here so that the shape is clear. Now what will happen because of this lone pair? Definitely the bond angles will change. Now next case, total bond pairs are 3 and lone pairs are 2. So A, again the geometry is trigonal bipyramidal only. Now 2 lone pairs we have to keep. So definitely we'll keep the lone pair at the equatorial position only. So one lone pair I am keeping here and second lone pair I am keeping here. Okay. Now this is bonded atom. Okay, you can see the geometry is still trigonal bipyramidal. So geometry is and what is the shape? Now for finding the shape we have to hide the lone pairs. It is in the form of T shape. And what is the example here? Now the example here is ClF3. It is like this. Okay, now one more case is possible where all the 3 are lone pairs. So when the total electron pairs are 5 in number, there are 4 cases. All are bond pairs, 4 bond pairs, 1 lone pair, 3 bond pairs, 2 lone pairs. Now one more case we'll discuss. So it is 2 and 3. Okay, now 2 are bond pairs and 3 are lone pairs. So this is A. Now at all the 3 places your lone pairs are there, at all the 3 equatorial places. Now B and B. And what is the shape now? Linear. Okay, so geometry is still trigonal bipyramidal, but the shape is linear, and the best example is XeF2, xenon difluoride. Now this is again an exception to octet rule, because according to octet rule noble gases do not make any compound, but here there is a compound of xenon, that is xenon difluoride. Now all the equatorial positions are occupied. Okay, so there is no place to keep the lone pair, so it's up to only 3 lone pairs. Now electron pairs are 6 are bond pairs and no lone pair is there. The geometry would be like this. Now these are the 4 bonded atoms. 1 bond pair is up and 1 bond pair is down. Now I will join them. Basically these are not joined. The dotted line is only for the purpose of showing. Now there are 4 equatorial bonds and this is axial bond. The angles are also 90 degree here. This is also 90 degree and this is also 90 degree. So there are 4 equatorial bonds and 2 axial bonds. All the angles are 90 degree only. This geometry is known as octahedral geometry because it is in the shape of an octahedron. Octa here does not mean 8. Octahedron is a shape having 8 faces. So this geometry resembles to that octahedron. That's why it is known as octahedral geometry, and it is shown by which molecule? SF6. The sulfur atom is in the center. There are 6 fluorine atoms like this. Now the next is total electron pairs are still 6, 5 bond pairs and 1 lone pair. Now just opposite to trigonal bipyramidal geometry where the lone pair occupy equatorial position, here the lone pairs will occupy axial position. So you can see 1 lone pair I have placed here. Now the geometry is still octahedral, but the shape is now square pyramidal, because if you hide this, it is a square and 1 pyramid. And the example is ClF5. Now the last example would be, because now only 2 axial positions are there, so 2 lone pairs maximum we can put. So 4 bond pairs and 2 lone pairs. So these are 2 lone pairs, and what is the shape? Square planar, and this shape is occupied by the molecule XeF4. And this is again your exception to octet rule, because this is a compound of noble gas, and according to octet rule noble gases does not make any compound. So this is all about your valence shell electron pair repulsion theory. So we have seen that the shape of a molecule depends upon the number of bond pairs and the number of lone pairs. If only bond pairs are there, the geometry is regular or symmetrical. But if lone pairs are also there, then the geometry is distorted and we have to look at the shape of the molecules. From this table, direct questions come. You have to simply learn the shapes of molecules, like what is the shape of ammonia molecule, what is the shape of water molecule, and definitely you have to learn the bond angles also. So this is the second theory in this chapter, and in the next video we'll discuss about the third concept regarding bonding.